Hello everyone. Today I'm going to present a paper titled Diagnosis of Mixed Infections with Swine Viruses using an Integrated Microfluidic Platform. In this paper, a microfluidic platform was designed and a semi-automated immunoassay system was developed to analyze the microfluidic chips. The assay was performed to detect 3 agents of contagious disease in swine. These 3 problems and 3 diseases was a variant of porcine reproductive and respiratory syndrome virus, a classical swine fever virus, and a porcine circovirus type 2. Related to the materials and methods, how they collected the blood samples. They used these blood samples from the subcutaneous abdominal vein of pigs, and this was used and diluted with phosphate buffered saline. Related to the semi-automated immunoassay system, the integrated microfluidic immunoassay system consists of 4 injection channels. Here we can see, as we can see in this figure, consists of 4 injection channels and 1 stripting channel. In addition, it consists of a LED system with a diffuser or with diffusing foil for uniform illumination, and it has also an integrated camera that allows to take photos of the chips. The entire process from the sample loading to waste removal is performed automatically. Here also we can watch the indicator. We have an indicator and a switch where it allows you to determine when it starts and when it finishes. Related to the microfluidic chip, this device was developed with a silicon-based mold, and they use PDMS to mold the chip. This device consists of 3 layers. The first consists of 4 inlets for injection. So here they could inject the secondary antibody conjugate, the substrate solution, the wash buffer, and airflow. And you can also put the samples in these bigger wells. In the second layer, it can be seen that the device it's divided into 4 units for 4 different samples, as we can see here. The 4 units for different samples, and each unit has 4 wells for the 3 tests and the reference or the blank. And the third layer shows the connection between the 16 wells where the waste is removed through a channel. So here we can see how the chip looks like, and also side view of the microfluidic chip, where we can see the throughout hole and the 3 layers. The communication vessels are an important part, but we can see it already an important part of the chip. So they also prove that these communication vessels are important or it's not necessary to put it. All the process begins by placing the diluted blood samples in the larger wells or the bigger wells, at which time the microchip was placed in the electronic device. After that, a wash buffer solution was injected, so it pushed the sample into the reaction wells. After that, they add a secondary antibody conjugate. In this case, they use gold anti-porcine conjugated, and they introduce in this step. After that, because of an excess was generated, because an excess was generated, which was removed with a wash buffer. And after that, they removed also with flush out with an airflow. After that, the substrate was added to the reaction well, and the removal channel was capped to prevent crosstalk. Finally, they could take the images were captured with the system after 3 minutes of reaction. In this figure, we can watch the design communication vessels for balancing the flow. And the analysis were carried out taking into account the electrical circuit models. That's why as an equivalent or as an equal system to compare the reagent distribution. In this figure, it is shown that the communication vessels helps to the uniform distribution of the reagents. And we can see in this graphic. This was determined with the observance analysis of the samples with and without communication vessels. So here we can watch that with communication vessels, they could keep the uniformity and precision of the reaction. The exposure time was also determined in the imaging, as shown in the figure. It is observed that the transmittance increase with the dilution concentration. To avoid under and overexposure was set between 1 and 200 seconds of exposure for the 3 tests, because it was proved with the 3 tests. Also, they compare the method in situ, and they compare with the laboratory tests. In the test, on-site tests were performed to compare with laboratory tests, and the analysis was performed manually, giving positive, negative, and indeterminate results with a sample value of 100. So it was proved also with the 3 tests. And these results were, as you can see here in this figure, it shows in vertical scatter plot of the results obtained by the microfluidic platform versus the results determined in the laboratory. Also, they determined with this the 3 important aspects like accuracy, sensitivity, and specificity. With this, due to the uniformity of values and precision of the automated immunoassay system, they determined that this is a good alternative to eliminate manual operational error, and comparing with traditional methods, the amount of reagents was reduced by 11 times. They don't use a big amount of reagents. That's why it's a good alternative to use this method. And determined a grade and accuracy greater than 93.8%, sensitivity greater than 88%, and specificity greater than 96%. So they take that as a reference of a great method or system that they can use on site to determine and reduce the time of the time they need to use to analyze all the results. So also including the microfluidic device have proven to be the best alternative to reduce this results delivery time, and of course preventing potential disease outbreaks for this reason. Thank you.